Hello and welcome. Today we're going to be talking about the arc length of parameterized curves in 2D. So let's recall what an arc length is. First, you always start with some t going from A to B, right? And this is going to be some time interval. And of course, then you're going to have x and y space. And then you're going to have a parameterized function, or what we'll call a curve. It's going to be x of t, y of t. Okay, there's our x and our y, and we can think that there's some curve in space where basically what's going to happen is at every point in time there'll be an x of t, y of t point, and then it forms this trajectory that will move through space over time. And you're going to go from x of A, y of A, all the way to x of B, y of B. All right, so we've studied these for quite a bit now at the beginning of our course, but we haven't really seen them much. Now they're resurfacing again. Obviously, as we're moving towards more work in higher dimensions, we're going to start seeing more of this kind of interesting spatial stuff. But the goal we have for today is actually going to be one of integration. And is actually, we want to find the arc length of such curves. So we'll call this curve C, right? So we want arc length of C. I can give it that name right there. And I can just also call it L. And I want to figure out how to actually get that. And we're going to use a trick that we've done so often, which is break up the line or the curve into pieces, and then approximate each piece by a line. Get the length. So we're going to, these pieces, and maybe we can think of these pieces as actually I equals 1 all the way to n. And then we're going to get these pieces of this line, and we're going to call these pieces Li. And of course, we're going to measure the distance. We'll call it Di of each. Actually, let's not call it Di, just because so many other things use the letter D. We're just going to call this distance Li. That'll actually be better. Okay. So I'm going to erase our Li and just say that the distance of each line is called Li. Okay. Measure the distance of each piece. And of course, L, the arc length, is going to be approximately equal to the sum of those Li, I from 1 to n. Okay. So let me just see if I can get a schematic of this up for you guys. There's x and there's y. And there's my curve. Okay, what I'm going to do is I'm going to break it up into pieces. Like that. And then I'll draw a line right there. That'll be L1, L2, L3, and L4. All right, so L is going to be approximately equal to the sum of I equals 1 to 4, in this particular case, of Li. All right, so what's the system here? Remember that x of t, there's this third variable, t, involved. So t was basically this time-like variable, okay? What we can actually do is, we can think of it as basically pieces of time. So what we can do is say t is actually equal to t naught, well, actually, it'll be equal to a plus delta t. So delta t will be our interval of time times I. And we're going to make it so that basically I, delta t then can actually be b over a over n, like that, right? So that ti, yeah, see, those are the ti's. So we can write it this way: a is plus b minus a over n of I. And we can take I going from 0 all the way up to n. Okay, cool. All right, so those are these different points, and of course there are n plus 1 of those partition points. Okay, fine. All right, and then from that, of course, we can take x of ti and y of ti, and we can actually just call those xi, yi. Okay? And we know that basically x0, y0, those are going to be that'll be basically the start. And then there's xn, yn, and that, of course, is going to be the end. Okay, good. All right, and now the li, well, let's think about that up close. We want to figure out what that is, but maybe what the best thing to do is just look at one example here. Here is xi, yi, and here is xi plus 1, yi plus 1. Right? So from here to here, a delta t time interval has elapsed. We can draw a line there, and we're going to make that li be the thing that we want. And li, of course, we should be able to get from Pythagoras. All we have to do is find the delta x, right, which is going to be xi plus 1 minus xi. And then there's also going to be a delta y. We can call these xi and delta, or sorry, delta xy and delta iy. And then that's going to be, of course, yi plus 1 minus yi. All right. Well, the distance should be, from Pythagoras, it should be delta xi squared plus delta yi squared. That'll be the length of that line. All right, so we have a change of x and we have a change of y over a period of time. This then should give us a really nice idea here, which is basically delta x. One thing I can do basically is multiply by delta t and then divide by delta t, right? And we know that, so that hasn't changed anything that's going on here, but what we can do is actually say that that's approximately equal to dx dt, delta t. Okay, we do the same thing for the y as well. That'll be approximately equal to dy dt, right? And basically, we're going to assume the curve is smooth, so that dx dt and dy dt are easy to compute. Okay, so most of all the examples we're going to look at, of course, these are readily available if you know some derivative or your differentiation rules. Well, that means that, remember, this is going to be delta x here, and this right here is delta y. So that means my li can actually be written as now approximately as the square root of dx dt times delta t, quantity squared, plus dy dt times delta t, quantity squared. And I can rewrite that actually as dx dt with the square root there, and that thing's all going to be squared, plus dy dt, all quantity squared. But then what we're going to do is put a bracket around that and put a delta t squared there. And of course, that can pop out the front or pop out the back and make that just a single delta t to the first power. And we get our, and I'll just write this in different notation. It'll be x prime squared plus y prime quantity squared. So that is our formula then for our Li. I think we have it here then. All we have to do then, of course, is add all these up. I'm a little out of room here, but I'll just write it. The arc length then is going to be the approximate integral, or the approximate sum of the xi prime quantity squared plus the yi prime quantity squared delta t. We're going from I equals 1 to n. Well, let me rewrite that then. If that's our kind of take-home message here. This is looking, of course, a lot like an integral. And of course, now all I got to do is take n going to infinity and delta t going to 0, or dt, actually. And then, of course, we have L is going to be equal to the integral from a to b of the integral, or of the function x prime squared plus y prime squared dt. Okay, and so the idea here is, of course, if this is your curve, you start out with a coarse partition like that. And of course, the L is not going to be very good, but then if you go to a finer partition, you're going to get a better approximation. And if you go to a finer still partition, you're going to get really close. You'll get closer and closer and closer as the number of partition points gets smaller and smaller and smaller until eventually you get the exact arc length from it. All right, so with that said, I think we now have this really nice formula for the arc length. The next thing to do is, of course, try it on a few examples. I'm going to try it on a circle. Of course, we remember that 2 pi r is the general formula for a circumference. All right, well, let's actually go ahead and verify that. Again, this is just a first example. So the circle, of course, is going to be x of t, y of t. If we remember how to make a circle, it's going to be r cosine t, r sine of t. Okay, and then t, of course, we have to go around a whole circle, so it's going to go around 2 pi radians. All right, well, x prime then, we need to get all the ingredients for our arc length formula, and that's going to be r negative sine of t. And then we have r, undo. And then, of course, y prime is going to be r cosine of t. All right, now, of course, we just take this r x prime squared, and then we're going to get an r squared sine squared t. And then a y prime squared is going to be r squared cosine squared t. Put them in the formula, and we have this. And what we're going to do is, of course, factor out the r of the square root. There'll be an r squared, but when we pull it out, the square root will take care of the square. And we have sine squared t plus cosine squared t. And we have, of course, another identity here, that sine squared plus cosine squared is equal to 1. So we have a very simple integral here. Two pi r. Of course, that's the familiar formula we know and have used extensively. We've simply verified a fact that we already knew. But again, I think the real picture here, though, that I want to develop is that we came up with a function that draws a circle, okay? And then we did all the work to plug it into our formula. And so I think that's the key here for this problem, is learning just the strategy of how to construct the integral, okay? And so a simple example is good, particularly at the beginning. All right, so now let's do maybe a slightly more complicated one. Let's do what's called the cycloid. Okay, so a cycloid is this sort of arch shape. Okay, so you get it by taking a circle of radius r, and if you put a pencil on it and then you roll this circle out, you roll it all the way out to 2 pi r, the circumference of a circle, right? And you basically track, I'll put it as a red dot there, you track where, eventually when it rolls to that position, you'll have done one full revolution. But if you track the actual position, x of t, or x of theta, let's say, y of theta, as it goes around, it'll make this arch shape as it goes through its cycle, okay? And that's called a cycloid. And there's a nice formula for it. It's x of theta is equal to r theta. That's the movement of the circle left to right as you're rotating it, okay? And then, of course, x is going to speed up and slow down, minus r sine theta. As it goes through its cycle, the x will also wobble back and forth a bit. And then, of course, y of theta is just going to be r of 1 minus cosine theta. Okay, so that's what draws the actual cycloid curve, are these two functions. And theta, of course, is going to range from 0 to 2 pi. Okay, all well and good. Let's put it in the formula. Now x prime, we're taking the derivative with respect to theta, is r minus r cosine theta. And y prime, of course, is going to be negative r sine theta, but we're going to take the positive because the derivative of cosine is negative sine. Okay, good. And now, of course, all we have to do is square these. So you're going to get an r squared minus 2 r squared cosine theta. Okay, so that's this whole thing squared. And then finally we get an r squared sine theta. Sorry, the cosine, oh, oops, I forgot one part. Plus r squared cosine squared theta. All right, so this part right there, that's actually just going to be r squared because of the Pythagorean trigonometric identity. All right, that looks good. So we put it all together. All of that together, we get 2r squared minus 2r squared cosine theta. We take the square root of that, and then we're integrating from 0 to 2 pi d theta. Of course, we can pull out an r from everything, from the square root. And then we get the root 2 minus 2 cosine theta, d theta. All right, so at this point, we're going to have to do a trig identity. It's not too hard, but let's just note one thing coming out of this, right? So first off, what we're going to do is we note that 1/2 1 minus cosine of 2 phi is equal to sine squared phi. And that will play really nicely in the square root there, right? So we're really close. So what we really need to do is actually say that 2 phi is equal to theta. So we're going to do a substitution here. So we're going to do a d theta d phi how should we do this? Well, any way you'll want to do it, maybe we'll say that phi is equal to phi over 2, right? So we're going to do a d phi d theta is equal to 1/2, otherwise known as 2d phi is equal to d theta. Okay, so maybe I made that more complicated than it need to be, but the idea is anywhere I see a d theta, I can put a 2d phi in its place. All well and good. Okay, all right. And when we do that, of course, we're going to half our integration interval. So now we have 0 up to pi now, because again, we've halved everything. And now we have a 2 out front because of the 2 in our substitution. And now we have 2 minus 2 times 1 minus cosine 2 phi d phi. Okay, so we're getting close here. The last thing we need to do before we really just go in for the ultimate here is we need that 2 to become a 1/2. So what I really am going to do is going to multiply it by a 4 and then divide by a 2. Like that. And again, we're going to get another 2 coming out. And now we can exploit the trig identity. That's going to be sine squared phi d phi, otherwise known as 4r, the integral from 0 to 8 of sine phi d phi. We take the antiderivative, which is going to be 4r times negative cosine phi, evaluated at 0 to pi, and that, of course, becomes, we've done this calculation a few times, but that's 2, okay? So 8r. So that's a nice formula. So the arc length of the cycloid, where you use a circle of radius r, will always be 8 times it. Oh, so that's a really nice special formula for the length of a cycloid. All right, so I hope these different examples have showed us how to build an arc length integral to do a job. And then, of course, we just got some more practice with our integration. I'll stop it there, and I hope this helped.